So on the worksheet called In Class Lack of Conservation, if we take a look at the fourth problem is very similar to the third problem that we did yesterday. There's just this kind of slight modification to it that I decided to scribble something up. So the fourth problem says that 10-kilogram baby is in their baby sled moving slowly at 2 meters per second at the top of a 15-meter tall hill that has friction. So yesterday's was frictionless, today we have friction. If you give them a 10 Newton push for 2 meters, so far the only thing that has changed, the numbers are identical with the exception of now there's friction. Blah, 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 energy is due to friction. Okay, there's a number, scribble out the number, I don't want that number in there. I'm going to make up a different number. How fast will they be moving at the bottom? Okay, so from this point, there is friction. They're going to lose some energy due to friction, but we are not using the number listed on the problem. So picture, here's my 10-kilogram baby. She is on top of a 15-meter tall hill. We push at 10 newtons for 2 meters before we either fall on her face or we just give up and let the baby go. And the baby's going to slide down a 200-meter long slope. That is not given in your problem. That's a new number. Okay? So we're saying the baby starts here and goes down a 200-meter long hill, which for the record, if you go up 15 meters and down 200, that's a pretty gradual hill, but whatever, it is what it is. The thing that we also need to add is there is a force of friction, and I'm going to tell you the value of that force of friction is 5 newtons. Two things that are not on in the fourth problem. We scribbled out some amount of energy lost due to friction, not using that number. But the thing we are using is on my diagram, which I should probably show the people on the camera, that the hill itself is 200 meters long. The sledding part of it, the hypotenuse, right? If this is a triangle, it would be our hypotenuse. This is where you actually slide down. And the force of friction is 5. The force of friction is 5. That number was not given in the problem. The question that is being asked is how fast are we going at the bottom of the hill? So it's a 2-location problem. We start at the top of the hill. We end, or the baby, I should say, ends at the bottom of the hill. V1, H1, V2, H2. It's a 2-location problem. We should also be thinking about spring stuff conveniently. We haven't mentioned springs yet, though. So, a couple quick things. If from here to here is 15, that's my H1, and if from here to here is 15, then from here to here is 0. We're trying to determine how fast they're going at the bottom of the hill, and it says that they were moving at 2 meters per second before you give them a push. Okay, so those are the information that we're going to start with. Have to add the force of friction is 5. That was not given in the problem. I ignored the number that was talked about. Energy lost due to friction. And I'm giving you the hypotenuse of this triangle, or the distance that the kid's going to slide down. And we're going to say that's 200 meters. So because it's a 2-location problem, it is a work in plus work done by friction is equal to change in mechanical energy. Now before we get too far along, let's first determine, is there work in and is there work done by friction? So on your formula sheet, there are a list of equations for the energy equations. And the second one talks about work in, and the third one talks about work done by friction. So for work in, we have to determine is there any work in, and we have to determine is there any work done by friction. And looking at our equation sheet, we could say work in exists if there's an applied force and a displacement. Are you pushing the baby over some distance? Yes. Therefore, there's work being put into the system. You give the baby a push, she's going to go faster because you pushed her. On the sled, You aren't pushing babies, I hope. If you pushing a baby on the sled down there. Is there work being done by friction? If you look at our equation sheet, there's work being done by friction if there's a force of friction acting over some displacement. And yes, there is a force of friction. There is friction, we should probably just say. So both of those are going to have to stick around. I like to calculate those numbers before I start plugging them in. I don't know why I do it with those, but not the energies. It's just what I do, I guess. So work in is equal to plus or minus the applied force times our displacement. And the work done by friction, I'm leaving a little bit of space here, is minus our force of friction times the displacement. Okay? Those are two things that we can calculate. So the work in is equal to applied force times displacement. I'm pushing the kid down the hill on the sled, and the kid's going down the hill on the sled. Is this the plus or is it the minus? Are they in the same direction or opposite direction? Same direction, so that's going to be the plus. My applied force is 10. What's the displacement for my applied force? 2. You push the child for 2 meters. So you are applying the 10 Newton force for 2 meters and only 2 meters, which means you're going to add 20 joules of energy to that baby. The baby's going to go faster because you gave him a push. That's that idea. Okay, so we now know that that work in number that we can plug into it is going to be positive 20. The work done by friction is always going to be a negative because friction always opposes motion. So this is always in the opposite direction of the motion, right? If the kid's going down the hill, friction pushes up the hill. So it's going to be minus. The force of friction is equal to 5. How far, what's the displacement of that force of friction? How many meters does friction act over? Could be 2, could be 200, could be 15. Those are the 3 meters one. So let's get rid of hopefully the obvious one. Does friction act over the 15 vertical meters? No, it's not 15. So it's really either 2 or 200. We push the child at 10 newtons for 2 meters, and then the child slides down the hill 200 meters. Does friction act over the 2 meters that you push and only the 2 meters you push? Or does friction act on a sledding hill down the entire length of the sledding hill? Entire length. So what's the displacement we need to use for the force of friction? 200. Yeah, we gotta use the 200. Okay? And that's really one of the big reasons I wanted to change this problem to reflect that. This was a number that was the energy loss due to friction. The way this problem was originally set up is we were just plugging a number into there, but I wanted to address that. That's the length of the hill kind of deal. So 5 times 200 is negative 1,000 joules. So friction removes 1,000 joules as the kid's moving down the hill. You push them, you add 20, but friction's going to remove 1,000 over the whole length of the hill. Now 200 meters is a pretty decent sledding hill for the record. It's pretty long. All right, now work in plus work done by friction is equal to change in mechanical energy. Before we start plugging numbers in, remember change in mechanical energy is my mechanical energy at location 2, ME2, minus my mechanical energy at location 1. So all my mechanical energy at the bottom minus all my mechanical energy at the top. Before I plug in any numbers, I would really encourage you to fully expand this equation because I feel by doing so, it kind of forces you to think about all of the energies, and it kind of forces you to ask yourselves the questions that I tried to teach you last. So work in plus work done by friction is equal to our change in mechanical energy, or our ME2 minus ME1, and this bracket is your ME2. This is your gravitational potential energy at location 2 plus our potential elastic energy at location 2 plus my kinetic energy at location 2. This is ME2. And it's minus my ME1, which is the sum of these three energies. My gravitational potential energy at location 1, my potential elastic energy at location 1, and my kinetic energy at location 1. Now, I start asking myself, what do we keep and what do we cancel? I've already discussed those two. We got to keep working, work done by friction. Positive 20, negative 1,000. We're looking for heights, we're looking for velocities, we're looking for spring stuff. So at location 2, I defined the height of the hill to be 0. At the bottom of the hill makes a lot of sense just to call the bottom of the hill 0, because then we only have one height. You could make it a number, but that's, if this was, like for example, if this was 10, then this isn't 15, this would have to be 25. We'd have to add 10 to our H1. So typically we just define the lowest point to be 0. At the bottom of the hill, there is no compressed spring. But at the bottom of the hill, the baby is moving in their sled. At the top of the hill, this is location 1, the baby had a height. There was no spring, but the baby was moving prior to me pushing the baby. Before I start plugging in numbers, I like to break down my energies. So the only thing left for ME2 is KE2, and that's 1/2 MV2 squared. That's my KE2. And that's going to be minus my PEG1, which is M times G times H1, plus my KE1, which is 1/2 MV1 squared. Okay. Now, order of operations when you get to that far side, in the green, we have to do the addition before we do the subtraction. We have to do what's in the parentheses or brackets before we do the subtraction. Just keep that. Work in was positive 20. Work done by friction was minus 1,000. And that's equal to 1/2 the mass of the baby, which was 10, times the V2 squared that we're solving for at the bottom of the hill, minus the mass of the baby, 10, times the gravitational acceleration on Earth, 9.8, times the height of the hill, which was 15, plus 1/2 the mass of the baby times the velocity of the baby at the top of that hill. There's a V2 here. That's what we're solving for, but that is the only unknown variable. That's the only V2, so nothing else can go with it except for this multiplication of 5 V2 squared. So we do some algebra. What is that? That's going to be negative 9,800 is equal to 5 V2 squared minus 1,470 plus 20. I'm pretty sure that's what those two numbers are. All right. minus 980 is equal to 5v2 squared minus, what is it, 1,490. Can't combine these two. I have to do the addition before I do the subtraction, so that's why this is 1490. Then, in order to get this to the other side, I can't combine these two terms, but I can add that to the other side. So if I take 1490 and I add it, I take 1490 and I subtract, if I subtract 1,000, sorry, if I take and I add 1490 to the other side, and then I subtract 980 from it. So I go 1490 minus 980, we get a value of a positive 510, which is equal to 5v2 squared. Divide both sides by 5, and we get 102 is equal to v2 squared. Last step, take the square root of that answer, and we get a V2 that's equal to 10.1 meters per second. It still seems higher than I thought. No, I think I did that right. Still made it a little fast for a baby, and a 20-pound baby in a sled, but it's better than 17 meters per second, I guess. So the intent of this one was to kind of illustrate that if friction is acting over the entire sledding hill, we need to make sure that we use the force of friction over the displacement of 200, not just the 2, because friction acts over the entire thing. Again, the way this problem was originally written, this was just a number that we plugged in a number for. The thing with an inclined plane, I can't give you a coefficient of friction because there's this normal force that's not perpendicular to this, or the normal force is perpendicular to the surface, but it's not equal and opposite of your force of gravity. So there's some issues when we get to those type of problems. So this is kind of the way we can do something like that. Questions that I can answer about that last problem before we move on? Okay, so like I had mentioned at the beginning of class, there is currently, currently I have 2 progress quizzes and I have 2 worksheets and a soccer div left for this kind of section between now and next week. This progress quiz, I had mentioned yesterday that one of the things that I expect you to be able to do is calculate the amount of power produced when climbing, say, a flight of stairs, or a sledding hill potentially, or a mountain, but it's the same idea that we did in Lent. The intent of this is for you to have an opportunity to try without, I'm going to ask you to not look at the Matthias question. Try to do this on your own for your break. I'm going to ask you to try to do this without looking at your lab. If you get stuck on something, use your resources. Ask me, ask a friend, look at your labs. Don't just blindly copy what you've already done, because on your test, this is an expectation that you can do a calculation like this, so here's a practice problem. So I tried to be funny and clever, and I probably was none of them when I wrote this, but you, 80 kilograms, are at George Street Hill sledding with your bestie. I don't know if we can call them besties anymore, but that's okay. You just rode your sled to the bottom of the hill, and you now must do the most dangerous part of sledding, walking up the hill. I don't know if George Street Hill is like it was when I was a kid, but it ended up being like a sheet of ice, and kids are screaming, like, well, physically screaming, but flying down the hill, and if you didn't get taken out while trying to walk up the icy, slippery hill, it was mission accomplished. You felt good about yourself because it was very treacherous. Still that way? No? Yes? Did anybody ever go to George Street Hill as a kid? So you get off your sled and look up the 15-meter tall hill and scope out the potential threats before you start your ascent. At the top of the hill, you stop and celebrate the fact that you didn't get hit by another sledder. If it took you 35 seconds, which probably is pretty quick to go up George Street, but whatever, I don't know the height of George Street Hill either. How much power did you generate? So this is a power calculation, and the calculation for this power is very similar to your stair power lab. So I would recommend that you try this without looking at any of those other things first. I do have the answers posted on that lab table right there. And right next to it is that another worksheet that I referenced. So there's a worksheet called Lack of Conservation 1. I do not have it built out in Canvas yet. I might get it built out yet this class period, we'll see. It is not due until the end of the Monday at 11:59. So it's not due tonight, it's not due on Sunday, it's due Monday night. So you probably have some time on Monday to work on it as well. But do this first, check your answer. If you have questions, please, please, please ask. Then grab that worksheet, and that's what I want you working on for the rest of the class period. If you have questions, let me know. If you get it done and I don't have it ready to submit yet, I'll try to my best to get it up and running.